Welcome to the Deep Dive. Today, we're embarking on a mission that I think is critical for anyone seeking real concept clarity in armament technology.
Absolutely.
We're doing a complete, structured revision of small arms systems. We're going to move systematically, building up from the core foundational definitions all the way to the cutting-edge technologies.
That's right.
Think of this, learners, as your shortcut to mastery in what is, let's be honest, a very complex field.
And this session is really focused on establishing an authoritative understanding. We're going to synthesize the technical principles, the mechanical operations, and of course, the performance metrics.
The how and the why.
Exactly. The how and the why that govern modern small arms. Our goal is to make sure you have absolute clarity on the definitions, the specialized language, and the critical relationships that link all these systems together.
Okay, so let's start right at the beginning. We need to establish the baseline definition. If you ask a military engineer what exactly are small arms,
Well, the definition is very precise. It's quantitative. Small arms are designated as weapons that have a caliber of less than 25 millimeters.
less than 25 millimeters, so that's the hard cutoff.
That is the hard dividing line. Anything above that, you're starting to get into light artillery.
Yeah.
But beyond caliber, there's a vital operational constraint.
Which is?
They have to be designed to be operated by just one or two people.
Okay, so that implies portability, rapid deployment. It's all about the soldier.
It's entirely soldier-centric in its design.
So if a weapon fits those two criteria, the caliber and the operator count, how do the armed forces then organize them? How do you classify them for, planning and logistics?
The classification is based on four interwoven factors.
Mm-hmm.
These really dictate everything from procurement all the way to tactical doctrine.
All right, what's the first one?
First, you have the inherent characteristics of the weapon itself. Its weight, its length, its range capabilities.
Or raw specs.
The raw specs. Second, and this is crucial, is its role in battle. Its tactical employment. Is it a primary infantry weapon? Is it a support weapon? Or is it something more specialized?
Okay, that makes sense.
Third is the mode of operation. This is the mechanics we'll be exploring in detail later on. Recoil, gas, or blowback.
The engineering behind it.
Precisely. And finally, the specific technical specifications. This covers ammunition, maintenance profiles, things like that. Those four elements together, they create the weapon's identity in the system.
That brings us to a bigger, more strategic question, doesn't it? The military requirement. Why are small arms still so fundamentally important? We're in an era of smart munitions, drones, precision artillery.
And it's a fair question. But they are absolutely essential.
Why is that?
Because while technology does progress, small arms fulfill tasks that, frankly, no other system can replicate.
Yeah.
They allow a very localized, very discriminatory and immediate application of force.
In places where a drone can't go.
Exactly. In cities, in dense forests, in tunnels. But there's a deeper reason, a more human reason. The small arm in a soldier's hand is arguably the single greatest factor in boosting their morale.
That's a fascinating point. So it's not just a tool, it's a psychological anchor.
It's the last line of defense. It's the primary means of survival and offensive action for that individual operator. It's everything to them.
Wow. So the technical requirement is linked directly to the psychological state of the combatant. Now, if we look at the decision-making, the procurement process, when planners decide on a new rifle, what are the 5 deciding factors that shape that requirement?
Okay, so when defining a new requirement, 5 elements must align perfectly. Firstly, tactical use.
So where's it going to be used?
Exactly. Defining the environment, the expected distance of engagement, who the primary enemy is. Secondly, data analysis from previous combat operations.
Looking at what worked and what didn't.
Right. Studying performance metrics, failure points, real feedback from the field. Thirdly, the chosen caliber of the projectile. This defines everything: impact, logistics, cost.
And the 4th?
Logistics. How easily can this weapon and its ammunition be supplied, maintained, interchanged throughout the entire operational theater? It's a huge consideration.
And I'm guessing the last one is the most obvious one.
It is. Accuracy. It's a non-negotiable requirement. It has to hit the intended target consistently. These 5 points drive the entire specification sheet.
And once that weapon is in service, how is its success graded? The sources mention 9 core characteristics that every system is judged by. It sounds like a real balancing act.
It is the ultimate engineering trade-off. We use these 9 core characteristics to evaluate the system's utility.
Let's walk through them.
We start with the desired effect on the target. So range, penetration, how far it can punch through material, and the wounding effect, which is terminal ballistics.
Okay, Effect on target. What's next?
Then we look at precision. That's accuracy, consistency. And for our learners, these are two very different concepts we're going to define very clearly soon.
Noted. So we have effect, precision.
Then mechanical performance. That's rate of fire and reliability. How often does it work when you need it to work?
Which is pretty important.
Critically important. And finally, the practical human elements. Weight and length.
How easy is it for the soldier to carry and use?
Exactly. And the perfect small arm, which, doesn't exist, would maximize all 9 of these. But in reality, if you enhance one, you often have to compromise on another.
Right. A classic engineering problem. So let's move from those abstract requirements to the actual hardware. Let's build a taxonomy, starting with the smallest, the pistol. What defines this category? It's not just its size, is it?
No, the defining trait is its intended operational role. A pistol is uniquely designed for one-hand operation.
Ah, okay. That's the key.
That's the key. And this design choice drives all of its other characteristics. It has to be lightweight, it has to have small bulk, and as a result, you have to accept a short, effective range.
But it must have something to compensate for that short range.
It does. It's designed for a relatively high rate of fire when needed.
Can you just quickly walk us through the basic anatomy of a service pistol, the key parts?
Certainly. Understanding this is foundational for any learner. Externally, you have the front and rear sights, the barrel, the main receiver, which houses the action, and of course the trigger.
And inside?
Inside, the critical cycling components are the recoil spring and the hammer. And the feed system is the magazine, which is typically inserted directly into the grip of the weapon.
Now here's a distinction that I think trips a lot of people up. It's about the fire control mechanism, the difference between a self-loading pistol and an automatic pistol.
This is a critical distinction.
Yeah.
It's all about weapon discipline and tactical deployment. Let's start with the automatic pistol.
Okay.
An automatic pistol is capable of continuous fire. It will produce a stream of bullets as long as that trigger is pressed right until the magazine is empty.
So, like a tiny machine gun?
In principle, yes.
Uh-huh.
But they're incredibly difficult to control. The inherent muzzle jump is so severe that any kind of accurate fire is pretty much impossible.
Which is why you don't really see them.
It is. They are rarely, if ever, used as standard service pistols.
So, conversely, the standard sidearm we see today is the self-loading pistol.
That's the workhorse. A self-loading pistol fires only one single round for each operation of the trigger.
One pull, one shot.
Exactly. To fire again, the operator has to completely release the trigger and press it once more. Most service pistols are 9mm, and they use the recoil principle to automate the cycling process.
So the recoil does the work of extraction, ejection, and loading the next round.
Correct. It makes it ready for that next trigger pull.
All right, let's move up the scale to the self-loading rifle, or SLR. Mechanically, it operates on the same fire control principle as the self-loading pistol, right?
Precisely the same. The SLR fires only one shot per trigger pull. The big difference is that it utilizes the much, much greater energy from the burning propellant of a rifle cartridge to automatically complete that entire reloading sequence.
So it extracts, cocks the firing mechanism, loads a fresh round.
All of it. It completely removes the need for the soldier to manually cycle the bolt after every single shot.
And this brings us to a really critical strategic decision. Why do the armed forces so overwhelmingly prefer the SLR, a semi-automatic weapon, over a rifle that can fire fully automatic?
This is a decision with deep tactical and logistical implications. It really boils down to two factors that underpin modern infantry doctrines.
Okay, what's the first one?
Higher accuracy. An aimed single shot offers a significantly greater chance of a hit than an uncontrolled burst. The fire is simply more lethal.
More effective.
Far more effective. And second, just as important, is ammunition economy.
Ah, the logistics tail.
Exactly. Full automatic fire, especially when a soldier is under stress, leads to a massive and wasteful expenditure of rounds. That puts a huge strain on the logistics chain. The SLR demands discipline, but it still offers a very high rate of controlled engagement.
And the performance metric for an SLR really drives that point home.
It absolutely does. It shows the true combat efficiency when you combine good training with good design. A trained soldier can fire up to 40 aim shots per minute with an SLR.
40 aim shots. That's a huge volume of effective fire.
It's far superior to just spraying a magazine wildly in the general direction of the enemy.
And the 5.56mm Incess rifle we'll talk about later, that's built around this philosophy.
It is. It deliberately incorporates a 3-round burst, or TRB, capability. This gives you a controlled volume of fire, but it mitigates that logistics burden you'd get from full auto usage.
Okay, finally in this conceptual layer, let's touch on the heavier support weapons. The machine guns. How are they categorized, and what's the big trend we're seeing in how they're used today?
Historically, machine guns are categorized into light, or LMG, and medium, or MMG, though we do still see heavy HMG and general-purpose GPMG versions in use.
And the DPMG is the jack of all trades.
It really is the platform of versatility. You can easily convert it to function like an MMG for sustained fire just by mounting it on a tripod, using a specialized sighting system, and often swapping in an extra heavy barrel to manage the heat.
What about the current tactical trend? How are these being deployed now?
We're seeing a notable return to using LMGs within the small, immediate tactical sections. It gives that fire team its own organic, mobile, high-volume suppression capability.
So the GPMGs are being pushed up the chain.
In a way, yes. The heavier belt-fed GPMGs are increasingly being reserved for dedicated support roles. They're used from fixed positions or mounted on vehicles rather than being carried by every infantry team.
Okay, so we've established what these weapons are and how they're used. Now let's get into the mechanical core, how they actually reload themselves. The foundation of all automatic operation is something called the operating cycle.
That's right.
What is this 10-step sequence, and why is it, as the source calls it, the heartbeat of every weapon?
The operating cycle is the mandatory sequence of actions a weapon must perform for every single round that is fired. It's universal. It doesn't matter if the mechanism is manually operated or fully automatic.
So for our learners, understanding these 10 steps is absolutely critical.
It's critical for maintenance and for diagnosing any weapon malfunction or stoppage. If something goes wrong, it's because one of these steps failed.
Okay, let's define these 10 essential operations. We'll go in order, starting just after a shot has been fired.
All right. Number one is unlocking. The breech mechanism is released from its secure, locked position against the barrel.
Step 1, unlock.
Step 2, retracting. The breech block starts moving backward, and it begins to draw the spent case out with it.
Okay.
3 is extracting. The empty case is pulled completely free from the chamber. 4, compressing. The return spring, which powers the forward movement, is compressed, storing energy.
And then you have to get rid of the old case.
That's step 5, ejecting. The spent, empty case is thrown clear of the gun's mechanism.
Makes sense, halfway there.
6 is cocking. The firing mechanism, the hammer or the striker, is reset, making the weapon ready to fire again. 7 is feeding. The next live round is moved from the magazine into the pathway that leads to the chamber.
So it's lined up.
It's lined up. 8 is chambering. The new round is pushed fully into the barrel breech, ready for firing. 9 is locking. The breech is secured firmly against the barrel extension to withstand the massive pressure of the next shot.
The reverse of step 1.
Precisely. And the final action, step 10, is releasing. That's when the firing mechanism is actuated, sending the projectile downrange, and the whole cycle begins again.
That systematic sequence. It's amazing that an automatic system can do all 10 of those steps, using energy that would otherwise just be wasted. Where exactly is that propellant energy harvested from?
We utilize the massive amount of energy derived from the burning gunpowder. And there are 2 primary sources we can tap into. The first is recoil energy.
Which is just the physical backward push of the weapon.
Exactly, the physical backward momentum.
And I believe that's only a tiny fraction of the total energy.
It is, you're right. Recoil energy represents only about 0.1% of the total energy input.
That's it, just 0.1%.
That's it. While it's minuscule, it's often sufficient to cycle smaller, lower-power systems, like many service pistols. But the dominant source, the one that powers most rifles and machine guns, is muzzle blast.
The gas escaping after the bullet leaves.
The massive expansion of high-pressure gases after the bullet exits the bore. That muzzle blast can dissipate up to 40% of the total energy produced.
Wow. So 0.1% versus 40%.
And that huge difference in magnitude fundamentally dictates which system an engineer has to choose for a specific caliber. You can't power a machine gun with 0.1% of the energy.
So engineers harness these 2 energy sources, the backward physical push of recoil and the energy in the expanding gas of muzzle blast, to power the 3 basic systems of automatic operation.
Correct. And those 3 distinct mechanical philosophies are blowback, recoil, and gas operation. Our deep dive now pivots to the engineering trade-offs of each one of these systems.
Let's start with blowback. Conceptually, this is the simplest system, but it uses this fascinating principle of the unlocked breech. What defines blowback?
Blowback, which is sometimes called spent case projection or inertial lock, is characterized by 2 things. The barrel is fixed. It does not move. But the breech block is not positively locked to that barrel during firing.
Not locked.
Not locked. The action relies entirely on the pressure of the burning propellant kicking back directly against the base of the cartridge case, and that's what forces the breech block rearward.
Okay, the critical question here is obviously safety. If the breech is unlocked, what stops the case from blowing out the back and injuring the operator when the pressure is at its absolute peak?
That is the entire function of the inertia lock. Safety relies solely on the physical inertia of a very heavy breech block mass and the resistance from the return spring.
So it's just weight and a spring.
That's it. The combined mass has to be sufficient to hold that breech closed for a critical millisecond, just until the propellant gas pressure drops to a safe level.
And then it can move back.
Then it can move back safely. This inherent design limitation is why the 9mm carbine machine is such a classic example of this principle. The cartridge is powerful enough to cycle the action, but it's weak enough to be contained by a reasonably sized mass of steel.
So simple blowback is really limited to low-powered cartridges. I understand engineers developed variations to apply the principle to slightly higher-powered weapons. Let's analyze the 4 key types.
Okay, the first is simple blowback, which is our baseline. It's purely mass and spring resistance, used strictly in low-power weapons like small pistols and submachine guns.
And then we get to the more ingenious designs. How does advanced primer ignition, or API, get around the need for that heavy breech block?
API is a brilliant breakthrough in timing. Instead of firing from a stationary closed breech, the round is fired before the bolt is fully seated in the chamber.
While it's still moving forward.
Precisely. The critical insight here is that the massive forward momentum of that moving breech block is used to counteract the backward thrust of the explosion. The energy of the firing event is first spent just arresting the bolt's forward travel. That is a revolutionary concept. You're using the bolt's own movement to achieve safety.
It is. This brilliant timing allows for a much lighter overall design than a simple blowback system would ever permit for that same caliber.
Truly clever. Yeah. Next, we have delayed blowback, also called hesitation blowback.
Delayed blowback introduces some mechanical complexity in order to reduce the necessary mass. It uses specific mechanical parts, usually levers or rollers, that are forced into recesses in the receiver.
And they hold it shut for a moment.
They hold the breech block shut for a minute, controlled fraction of a second. The delaying force is at its greatest, precisely when the gas pressure is highest, and it tapers off as the pressure drops. The efficiency is immense.
How immense?
A successful delayed blowback design can reduce the necessary breech block weight to just 1/16 of the weight required for a comparable simple blowback system. 1/16. That is incredible. And the final variation is the most complex hybrid, blowback with a locked breech.
This system temporarily locks the breech physically, just like a recoil or gas system would during that high-pressure phase. But instead of being unlocked mechanically,
Let me guess, the gas does it.
the breech is deliberately unlocked by the residual gas pressure itself, causing it to blow back and cycle.
That sounds complicated.
It is. While this allows for the lightest possible breech block with high-powered rounds, it's extremely complex to manufacture, and it's notoriously sensitive to tiny variations in ammunition quality. The unlocking timing is just so fine.
So if we zoom out for a moment, what are the overall pros and cons of the blowback system as a whole?
The advantages are all about its simplicity and its cost. Blowback is fundamentally cheap, it's robust, it's simple to engineer, and it's reliable. And since the barrel is fixed, changing a barrel is also very simple.
But the disadvantages, they really seem to limit its application in a military context.
Absolutely. The disadvantages are significant. Firstly, it requires a heavy breech block in all but the most specialized variants.
And that big, heavy part moving back and forth.
It results in highly inaccurate fire due to the movement and the vibration. It's unsuitable for long ranges, and, critically, it offers no means of adjusting power. You can't compensate for fouling, extreme cold, or poor ammunition.
And the AFV problem.
Yes. Because the breech opens immediately, it's completely unsuitable for use inside armored fighting vehicles due to the immediate release of toxic fumes into the crew compartment.
Okay, so blowback is limited by that heavy unlocked breech. For high-powered service rifles and machine guns, we have to move to systems where the breech is firmly locked during that high-pressure phase. Let's start with recoil operation. How does the principle here fundamentally differ from blowback?
The core difference is the lock and the movement of the barrel. In recoil operation, the barrel is mounted as a free fit inside the weapon body, and the breech block is firmly locked to the barrel during firing.
A positive lock.
A positive mechanical lock. We utilize Newton's third law. The locked barrel and breech block unit moves backward together as a single mass, all due to the reaction force, the recoil energy.
So the whole firing assembly travels backward first. When does the system actually break that lock?
After that initial, short rearward travel, the barrel is mechanically stopped. The breech block, however, unlocks and continues moving backward using its stored momentum.
And that separation allows the rest of the cycle to happen.
Exactly. That separation lets the block perform the rest of the operating cycle, extraction, ejection, cocking, before the spring returns it forward to load a new round and relock. The positive lock during peak pressure is what makes this system vastly safer and more capable of handling powerful rifle and machine gun cartridges.
Now, recoil systems are subcategorized by the distance that lock unit travels together. This leads to long recoil and short recoil. What are the practical implications of that travel distance?
In long recoil, the bolt and barrel travel backward a distance that is greater than the length of the unfired round.
So a very long movement.
Very long. The bolt is then mechanically held back while the barrel is forced forward first by its own separate spring. This sequence is necessary to reduce stress on the weapon's mounting, but it results in a very slow rate of fire.
And I imagine all that barrel movement isn't great for accuracy.
It causes significant, unavoidable sighting problems. It's just not suitable for high-precision weapons.
Which is why short recoil seems to dominate modern designs.
It absolutely does. In short recoil, the breech remains locked only for a short, controlled travel distance, just while the pressure is highest. Once that pressure drops, they separate immediately.
And the benefit of that?
This minimal movement permits a high rate of fire, and it's significantly more accurate than the long recoil design because the moving mass and the barrel disturbance are minimized.
Now, to ensure reliability, especially on systems that fire a lot, engineers often add recoil boosters. Can you detail the two main types?
We can enhance the available energy with a recoil intensifier. This is a specialized chamber located at the muzzle.
How does that work?
It traps the propellant gases that follow the bullet, and it uses them to provide an extra push backward to the barrel. This ensures the system cycles even when it's dirty or you're using lower power ammunition.
And the second type?
The second type is the accelerator. This is a mechanical component, a lever or a claw, that actually transfers energy from the recoiling barrel to the breech block, speeding up the block's rearward movement.
To increase the rate of fire.
To increase the overall rate of fire, yes.
Okay, let's transition now to the third and a highly specialized system, gas operation. This is the method we see in most modern assault rifles. How does it harvest energy compared to the other two?
Gas operation is unique because it actively taps the high-pressure propellant gas. It taps it directly from a port that's drilled into the barrel.
So it's bleeding off gas from inside the barrel.
Exactly.
Yeah.
As the bullet passes this port, a portion of the gas bleeds off into a gas cylinder, and it drives a piston. That piston then strikes an operating rod, which performs the mechanical actions to unlock and cycle the breech block.
I understand the location of that gas tap is a really critical engineering decision. Why does its position closer to the breech or closer to the muzzle matter so much?
It's a major trade-off between pressure, heat, and fouling. Gas taken off near the breech is hotter and at a much higher pressure.
Which sounds good.
Well, the gas is cleaner because the carbon remains fully gaseous, which reduces fouling. But the high pressure causes greater erosion on the components, and it requires a heavier piston system to handle it.
Okay, so what about taking gas near the muzzle?
Gas near the muzzle is cooler, but this drop in temperature causes the carbon to solidify, to desublimate. This leads to significant fouling and carbon buildup in the system.
So there's a sweet spot.
There is. The engineering compromise for optimal reliability is usually struck somewhere between 20 and 30 centimeters from the muzzle.
And the mechanism driven by that gas comes in 3 distinct types. Let's compare them.
We can begin with the long-stroke piston. Here, the piston is physically connected to and moves the full distance with the breech block.
Okay, a single moving part.
Yes, which makes the system extremely robust. It's very common in machine guns. But the heavy, long-moving parts significantly disrupt the stability of the weapon.
Which is why it's not ideal for a rifle, leading to the preferred system, the short-stroke piston.
Correct. The short-stroke piston moves only a very short distance, sometimes just a few millimeters. It imparts a sharp, powerful blow to a separate operating rod, which then throws the breech block backward.
And this is better for rifles because...
It's preferred for rifles because the weapon's center of mass is minimally disturbed. This greatly maintains weapon balance and the stability of aim during rapid fire.
And the final gas system is the lightest, but also the dirtiest. Direct gas action.
Direct gas action eliminates the piston entirely. The gas just travels through a tube and blows directly onto the bolt carrier assembly itself.
Which must make it very lightweight.
It creates the lightest possible moving mass, but it has a very serious drawback. It deposits corrosive carbon residue and fouling directly into the sensitive mechanism and receiver. This leads to higher maintenance and a greater potential for stoppages.
So if we compare all three operating systems, blowback, recoil, and gas, what is the single biggest operational advantage that gas operation holds over the other two?
Its adaptability is simply unmatched. Gas operation is the only system that can genuinely and reliably regulate the power available.
Through the gas regulator.
Exactly. Engineers incorporate a gas regulator that allows the operator to control the flow of gas to the piston. This is essential for compensating for variables like heavy fouling, extreme cold or heat, or variances in ammunition quality. It ensures dependable operation in conditions that would just stop the other systems.
So gas operation wins on adaptability, but what does recoil offer that gas can't, especially for specialized vehicles?
Recoil-operated systems are exceptionally sturdy, and critically, they are the standard for weapons used inside armored fighting vehicles, or AFVs.
Because of the fumes.
Because of the fumes. A recoil system maintains a fully locked breech until the internal pressure drops to ambient limits. This means no toxic propellant fumes are immediately vented into the crew compartment.
Whereas a gas system vents right away.
It vents fumes immediately through the mechanism. It's completely unsuitable for AFV use. Plus, gas systems typically have a much more complex procedure for changing barrels, as the whole gas block assembly has to be mated correctly.
We've moved from the mechanism to the output. Now we need to focus on the science of hitting the target. Let's tackle two terms that are often used interchangeably, but have very specific technical meanings: accuracy and consistency.
This distinction is absolutely paramount in precision analysis. For all our learners, this is key. Accuracy is the ability of the weapon system, with proper sight adjustment, to apply rounds exactly to the point of aim.
So hitting the bullseye.
Hitting the bullseye when the sights are set correctly, that's accuracy.
And consistency.
Consistency is the measure of the weapon's internal quality and the ammunition's uniformity. It is the ability to apply rounds reliably to the mean point of impact, or MPI.
Which is the center of the shot group.
It's the geometric center of that pattern of shots, the group. Consistency is measured solely by the size of that spread. If the group is tight, the weapon is consistent, regardless of where that group is on the target.
So the goal for any new system design is sequential. You have to get the tightest group first, and only then do you worry about aligning that group with the target.
Exactly right. A system must first achieve excellent consistency, a tight, repeatable group. Only then can the operator use the adjustable sights to shift that tight group onto the aiming point to achieve the required accuracy.
What are the four major pillars that influence a bullet's flight path and ultimately determine where it impacts?
These four pillars influence absolutely everything. First, you have the firer. Their training, physical condition, and motivational level are all crucial for consistent weapon handling.
The human factor.
The human factor. Second, the weapon itself. Its design, its maintenance status, the quality of the rifling in the barrel, assembly tolerances, and of course the sights. Third, the ammunition.
Let's expand on that. How do tiny, invisible variances in ammunition translate into dispersion downrange?
Well, manufacturing variances in ammunition are a primary cause of inconsistency. Subtle differences in the propellant load or the weight of the bullet lead directly to variance in muzzle velocity.
And if the velocity isn't consistent,
the trajectory changes. This causes significant dispersion downrange. And finally, the fourth pillar is external factors. The environment, specifically air resistance, which continuously slows the bullet down, and gravity, which pulls the projectile down with an ever-increasing rate throughout its flight.
Once the firing mechanism is released, the bullet starts its flight, but the weapon itself moves. We know recoil is the rearward force, but this action also creates muzzle movement. What are the three mechanical factors that combine to create this destabilizing movement?
Recoil is the primary rearward reaction force applied through the base of the cartridge case. This force causes the muzzle to move because the force is almost never applied perfectly in line with the rifle's bore.
There are offsets.
There are three key offsets. First, the physical displacement of the weapon's center of gravity from the central axis of the bore. Second, the displacement of the butt from the bore axis. And third, the rotation of the firer about their hip, caused by that intense backward force transferring momentum to their entire body.
And when you're firing automatically, this cumulative effect is devastatingly visible. It's called muzzle jump. Why does muzzle jump fundamentally prove that perfectly accurate automatic fire from a handheld shoulder weapon is a mechanical impossibility?
Muzzle jump defines the absolute limitation of automatic infantry fire. The sequence is fixed. The first bullet in a burst hits where the operator aimed.
As it should.
But the immediate rapid recoil and vibration cause the muzzle to rise, and to rise rapidly. Because the automatic system fires so quickly, the second and all subsequent shots in that burst will inevitably leave the barrel on a trajectory pointed higher than the correct line of sight.
And a human can't counteract that force quickly enough.
No human can. Therefore, the weapon simply cannot produce perfectly aimed automatic fire.
We also need to look at how external factors apply to the weapon, not the bullet effect precision. What happens to the point of impact if the cartridge or the barrel is oily?
This is a classic maintenance failure with very clear consequences. An oily cartridge or barrel drastically increases the back pressure on the breech block. This causes the muzzle jump value to become extremely erratic.
So the impact is inconsistent.
Highly inconsistent.
Yeah.
But generally, the bullets will hit above the point of aim until all that oil residue is entirely burnt off and the system stabilizes.
What about adding something to the weapon, like fixing a bayonet for close quarters?
Fixing a bayonet changes the weapon's dynamics dramatically. It adds weight to the forward section, altering the overall balance and shifting the center of gravity forward.
And that causes the bullet to hit.
It causes the rifle to pivot differently during recoil, resulting in the bullet consistently hitting low compared to the point of aim.
Finally, on this point, let's address the critical role of physical support. How does the location where a soldier rests the weapon affect where the bullets land?
The placement of support is absolutely critical. If you support the weapon in front of its center of gravity, say, near the muzzle, the resultant jump will cause the bullets to hit high.
And the opposite is also true.
Conversely, if the weapon is supported behind the center of gravity, near the butt or the magazine, the bullets will hit low. This is why using the magazine itself as a rest, which soldiers are often tempted to do, invariably results in low impacts.
All right, let's shift now to the protective systems. The things designed to keep the soldier in the fight. Modern body armor technology. It's heavily reliant on synthetic, high-strength materials now.
Yes, the revolution really came with aramid fibers. These are man-made plastics that deliver immense strength relative to their weight. Lightweight mobility is paramount for the infantry soldier, so maximizing protection while minimizing the mass is the constant engineering driver.
When procuring body armor, protection is defined by the specific type of threat. What are the three distinct categories of physical protection the armed forces require?
The three types are distinct by the damage mechanism they're designed to counter. First, you have ballistic protection, which is designed to stop bullets, and it's rated rigorously by the specific caliber and type of ammunition it can successfully defeat.
Okay, stopping bullets, what second?
Second is edged blade protection, or step protection. This counters things like knives, broken glass, or sharp fragments. It often utilizes layers of fine chainmail.
And third?
Third is spike protection. This counters pointed, narrow threats like needles or screwdrivers. It requires specialized, rigid layers of plastic laminate to prevent that kind of penetration.
Beyond traditional plates and soft armor, the sources highlight two truly advanced concepts: liquid body armor and the powered exoskeleton.
Liquid body armor is a fascinating composite concept. It's based on something called shear thickening fluid, or STF.
How does that work?
This fluid contains hard, abrasive particles that are suspended in a liquid medium. Upon a high-velocity impact, like from a bullet or fragmentation, the fluid instantly transitions into a rigid, solid material. Instantly. It's low cost, it's lightweight, and critically, because it's a liquid when it's not being impacted, it doesn't restrict the soldier's natural movement or endurance.
And the powered exoskeleton. This sounds like something out of science fiction.
It's getting there. The exoskeleton is a wearable, mobile machine. It uses motors and hydraulics that sense the user's motion. Its purpose is to provide physical support to key joints, the shoulders, waist, and thighs, and by doing so, significantly increase the soldier's strength and endurance.
For carrying heavy loads or moving long distances.
Exactly. Carrying immense combat loads without fatigue.
We also see specialized protection for fixed positions, like anti-terrorist bulletproof glass. What are the two types, and what enables that famous one-way property?
The two types relate to splinter management. You have low spall, or LS, which uses glass on both sides to minimize splintering inside the protected space. Then you have no spall, or NS, which uses glass on the threat side and a thick layer of polycarbonate on the protected side.
And that stops all splinters.
It ensures absolutely no splintering enters the crew space. The unique one-way property is an asymmetrical design. It allows a person inside to fire back, penetrating the glass outwards, while the attacker's bullets, specifically those under 7.62 millimeter caliber, cannot penetrate from the outside.
Now let's return to the indigenous rifle system, the 5.56 millimeter INSAS family. What weapons make up this family, and what was the main driver for its design?
The INSAS is a standardized family of 3 weapons. You have the assault rifle, which is available in fixed or foldable buttstock versions, the light machine gun, or LMG, also fixed or foldable, and the compact carbine, which is foldable.
And the design goal?
The primary design goal was efficiency and mobility. Compared to the previous service rifle, the 7.62 millimeter 1A1, the INSAS achieved massive logistical savings. It's significantly lighter, more compact, and features 70% less recoil.
70%? That's a huge improvement for the soldier. Let's detail some of the specific engineering features that highlight its modern design.
Well, the manufacturing process prioritized cost and speed. The weapon's main housing body is constructed from pressed sheet metal rather than expensive machine steel.
And that's possible because of the locking system.
It's viable because the stress of firing is minimized on the body itself. It uses a front locking system, a rotating block breech with 2 lugs that engage a heavy barrel extension. This means the primary stresses are absorbed by the barrel assembly, not the housing.
And the soldier interface features seem designed for modern tactical awareness.
They are. It incorporates beta light sights, which are iron sights embedded with glowing dots for reliable night aiming. The furniture, the butt, grip, handles are all made of durable, modern plastic polymers.
And the magazine is a key feature.
The most cited tactical feature is the translucent plastic magazine. It allows the soldier to get an instant visual verification of the number of remaining rounds. That's a significant operational advantage for tactical awareness.
And what is the mechanism of the INSAS, tying it back to our earlier discussion on operating systems?
It is a gas-operated system. It utilizes a closed breech action, which means the bolt has to be fully forward when it's ready to fire. It features that essential gas regulator for reliable function in adverse conditions.
And the 3-round burst.
And as we mentioned, it employs the 3-round burst, or TRB, control mechanism. This ensures you get the required volume of fire while strictly adhering to the armed forces' demand for ammunition economy.
The armed forces are continually updating their inventory. Let's look at the new standard assault rifles entering service, starting with the Sig Sauer 716.
The Sig 716 is chambered in the powerful 7.62 by 51 millimeter NATO round. This signals a clear requirement for greater stopping power and an extended effective range of up to 500 meters.
And mechanically?
Mechanically, it operates using a highly advanced short-stroke gas piston system, which, as we noted, is preferred for maintaining weapon balance and stability of aim. Its highly modular design, with full Picatinny rail integration, makes it exceptionally adaptable.
Conversely, we have the modernized classic, the AK-203. It keeps that Kalashnikov legacy, but with modern enhancements.
The AK-203 is designed to retain the legendary ruggedness and reliability of its predecessors, while significantly enhancing the ergonomics for the modern soldier.
And its specs?
It's chambered in 7.62 by 39 millimeter, offering a reliable engagement range of 300 meters. Crucially, it employs a long-stroke gas piston system.
So that's a different design philosophy.
It is. It's a philosophy that prioritizes ultimate reliability and simplicity over minimal muzzle movement. This system is now being manufactured locally as part of the Make in India initiative, and it weighs 3.8 kilograms.
So the difference between the SIG's short stroke and the AK-203's long stroke really highlights the different engineering priorities: precision versus robust reliability.
An excellent way to put it.
Moving to support weapons, the Carl Gustaf MKAV recoilless rifle has undergone a dramatic logistical upgrade.
The MKAV represents a massive leap in portability. By using advanced materials, specifically titanium liners and a carbon fiber casing, the weight of the system has been reduced dramatically to just 6.7 kilograms.
And it has a new feature for maintenance.
It does. Beyond portability, its integrated shot counter provides invaluable logistical information. It allows maintenance crews to accurately track the system's life cycle and prevent failures in the field.
Let's look at a specialized machine gun, the Enegy LMG, which is designed for sustained, heavy firepower. This weapon uses a distinct mechanical concept called the open breech mechanism. What is its purpose?
The open breech mechanism is a design solution specifically for weapons that are expected to deliver massive, sustained volumes of fire. When the Negev is ready to fire, the bolt stays in the rearward or open position.
The round isn't in the chamber yet.
It's only chambered when the trigger is actually pulled. This open configuration serves a vital cooling function. It prevents a live round from sitting in a superheated chamber, which could cause cook-offs, and it helps cool the barrel during heavy use.
And what are the other critical operational features of the NED-UV?
It's powered by a reliable long-stroke gas piston. It offers excellent versatility with 3 firing modes: safe, semi-auto, and full auto. It features an adjustable gas regulator, allowing the operator to fine-tune its power output, and it's belt-fed for maximum sustained fire.
Shifting now to extreme precision, we have the Sacco sniper rifle. It's capable of accurate engagement at 1,200 meters. This distance demands a system that eliminates almost all variables, which leads to the use of a manual bolt-action mechanism.
The reliance on manual bolt action is the fundamental technical reason for its superior accuracy at these extreme ranges, especially using powerful ammunition like the .338 Lapua Magnum.
Because automation introduces variables.
Exactly. Moving pistons, unlocking lugs, they all introduce tiny inconsistencies. A manual bolt action removes them. For every single shot, the operator manually performs the essential steps.
Walk us through that.
You pull the bolt handle up and back. That ejects the spent case and cocks the firing mechanism. Then you push the bolt forward and down. That feeds the new round and critically positively locks the bolt with extreme tightness before firing.
And that solid manual lock is the key to consistency.
It ensures a level of consistency far beyond what any automated system can achieve.
Finally, let's turn to the indigenous compact weapon, the ASMI submachine gun. What role was this developed to fill?
The ASMI, which means pride, was designed as a modern, compact personal defense weapon, or PDW. Its primary mission is to replace the severely aging 1A carbine, a legacy weapon that's been in service since the 1960s.
And its mechanism.
It operates on the blowback principle, a simple, high rate of fire mechanism. It's chambered in 9 by 19 millimeter rounds at 600 rounds per minute. Its compact size and reliance on blowback make it ideal for fighting in confined spaces, like urban areas or vehicular combat.
To conclude this inventory review, let's look at the future of ammunition design, specifically focusing on reducing the soldier's load.
The 2 major trends here are cased telescopic ammunition, or CT, and polymer cartridge cases.
Tell me about CT ammunition.
CT ammunition encapsulates the projectile completely inside the cartridge case. This structural change drastically reduces the overall length and cuts the weight by a massive 33%.
And it helps accuracy.
It does. By eliminating the traditional neck of the case, it enhances accuracy by reducing the center of gravity, or CG throw, during the initial launch phase.
And polymer cartridge cases.
This is more straightforward. By replacing traditional brass or steel with high-strength polymers, you achieve a weight reduction of 25 to 30% and lower overall production costs. It's a major logistical benefit for the supply chain.
We are now at the conceptual frontier, exploring design trends that prioritize ergonomics and modularity. The Israeli Tavor assault rifle is a great example of this approach.
The Tavor is absolutely designed around the soldier. Its ergonomic shaping ensures it's perfectly balanced, enabling accurate single-hand operation.
And the sights are a key feature.
It integrates optical sights that allow accurate aiming and firing with both eyes open. That's a huge advantage for situational awareness. And its compact design makes it exceptionally effective in tight enclosures.
A core design feature of the Tavor is the bullpup layout. This radically changes the rifle's silhouette. How does locating the mechanism behind the trigger offer such a great advantage?
The bullpup configuration places the magazine and the entire firing mechanism behind the trigger group. The primary advantage is length reduction. The weapon achieves a 30% shorter overall length while, and this is critical, retaining the full, long barrel length.
Which maximizes velocity.
It maximizes velocity. This layout also provides better center of gravity management, centralizing the weight for higher accuracy in bursts. It's ideal for fibula fighting in built-up areas in close quarters battle.
But that compactness must come with some sacrifices, especially for the operator.
It does. Because the explosion and the ejection port are physically closer to the firer's face, things like noise, gas, and hot brass become immediate concerns. Also, the magazine change procedure can be unwieldy and non-intuitive compared to traditional layouts.
For highly specialized urban scenarios, we have the corner shot system, which solves the problem of exposure.
The corner shot is purely an urban warfare tool. It allows a soldier to see and attack targets up to 60 degrees around a corner without exposing their body to enemy fire.
And it does this with a camera.
It uses a high-resolution camera mounted on the pivoting barrel section, which feeds to a monitor. And it utilizes a remote trigger control system. It's effective for the precision application of force up to 250 meters.
Now, for sustained high-volume fire, the old concept of the Gatling gun is very much alive in modern warfare, but for a specific technical reason, preventing overheating.
The genius of the Gatling gun is its rotating barrel assembly. Since each barrel fires only one shot as it rotates into position, the other barrels are allowed time to cool down rapidly. This mechanical heat mitigation allows for continuous, exceptionally high rates of fire.
And modern versions are powered.
Modern versions, like those on aircraft, are typically driven by electric motors to achieve these sustained, massive rates of fire.
Looking to the horizon now, let's analyze directed energy weapons, or DDWs, the true beam weapons. These are designed to hit targets instantly and cheaply. What are the three categories?
The three technological streams are distinct. First, you have laser-based systems, which use photons for direct, highly focused thermal or structural damage. Second, high-power microwaves, or HPM, which use intense radio frequency power to specifically attack and disrupt electronic systems.
And the third?
Third is charged particle beams, or CPB. These accelerate subatomic particles to very high velocities, delivering massive kinetic energy upon impact.
We're also seeing extensive development in non-lethal weapons, or NLWs. They're designed to stop personnel while minimizing permanent injury. What are the four operational categories NLWs are designed to address?
NLWs are categorized by their target effect. They are anti-sensor systems, which disrupt vision or optics like low-energy lasers, anti-mob systems designed to slow or halt vehicles or crowds like specialized sticky foam barriers,
What else?
anti-command and control systems, which are primarily HPM weapons designed to attack electronic communications, and anti-infrastructure weapons designed to attack structures using methods like liquid metal embrittlement.
The most famous example of NLW is the pain beam, or active denial technology. How does this weapon induce a safe, immediate deterrent effect?
It exploits the body's natural pain reflex by transmitting highly focused electromagnetic energy. This energy heats the water molecules just below the skin's surface to a depth of less than 0.04 centimeters.
So very shallow, but it feels hot.
It causes an immediate, intense burning sensation, which forces the target to instinctively move away. The key is its rapid action. Most targets reach the pain threshold and retreat within 3 seconds, making it an extremely effective deterrent.
Finally, we have to touch upon the most ethically challenging frontier: lethal autonomous weapons, or laws. These systems operate independently, but why do they raise such significant legal and ethical concerns for the armed forces?
Laws are systems that can independently search for, detect, and engage targets based on pre-programmed constraints without continuous human intervention.
And we have defensive versions already.
We do. Defensive examples like the Phalanx anti-missile system or Iron Dome must react autonomously because of the sheer speed of the incoming threat. But the ethical and legal concerns are massive. They revolve around accountability if civilians are harmed, the risk of excessive force application by machines, and the crucial lack of human emotion and judgment.
Which you need to navigate the complexities of the battlefield.
The complex, unpredictable, and morally ambiguous situations on the battlefield.
We'll conclude our deep dive by examining the eyes of the weapon, the sighting systems, which ensure the bullet goes where the soldier intends. What are the four types of systems utilized today?
The four types are open sight, aperture sight, optical sight, and lensatic sight. They really represent a progression from simplicity to complexity.
Let's start with the open sight, the classic V-notch and post. What is its advantage and its main drawback?
Open sights are simple, and they are the fastest to bring into aim for rapid engagement. However, they are highly prone to alignment errors, especially if the sight radius is short. The operator struggles to accurately center the front post within the rear V-notch.
And the aperture sight solves that alignment problem, correct?
Yes, it does. The aperture sight uses a circular hole in the rear sight. The shooter's eye naturally and automatically centers the front sight post within that circular aperture. This significantly reduces alignment errors and improves consistency.
And it's good in low light.
It's excellent in low light conditions because the eye's pupil automatically adjusts to center the light source within the hole.
Now for the key distinction between the two advanced systems, optical sight versus lensatic sight. What is the fundamental difference in function?
The optical sight uses multiple lenses to optically superimpose the target and the aiming mark, or graticule, onto the same focal plane. This essential feature is what allows the sight to provide magnification.
So it's a telescopic sight?
It functions as a telescopic sight, which is universally required by snipers to extend their effective engagement range. The drawbacks, of course, are that they're fragile, they're heavy, and they're susceptible to misting.
And the lensatic sight.
The lensatic sight uses a simpler single convergent lens combined with a translucent graticule. And crucially, learners must remember this. It provides no magnification.
So what's its advantage?
Its advantage is that it allows for easy, rapid aiming while keeping the firer's eyes set to the surroundings. You maintain better peripheral situational awareness compared to the tunnel vision you get with a high-powered optical scope. You've now completed a thorough revision of the layers of small arms technology. To quickly summarize our journey, small arms are defined by their caliber and their mission, driven by 5 core requirements including tactics, logistics, and accuracy.
Then we move to the mechanics.
Automation relies on the foundational 10-step operating cycle, powered by recoil or muzzle blast. This manifests in 3 major mechanical systems: the heavy, simple, unlocked blowback, the sturdy, locked recoil system, and the adaptable regulatory gas operation.
And getting the shot on target.
Precision demands optimization of both consistency, which is the tight group, and accuracy, the correct placement of that group. This means countering destabilizing forces like muzzle jump and support location effects.
And finally, the modern inventory and future tech.
Finally, the armed forces are rapidly integrating modular systems like INSAS, SIG, and ASMI, alongside advanced protective and technological frontiers like liquid armor and directed energy weapons, all supported by sophisticated sighting systems like the aperture and optical sights.
That structural revision brings us to our final thought for you to explore, learners. We analyzed the AK-203 with its 300-meter effective range, which uses the highly reliable gas operation system, and then we looked at the Seco sniper rifle with its 1,200-meter range, which requires the shooter to use a manual bolt action for every single shot.
A huge difference in both range and operation.
The Seco is 4 times more accurate, but it sacrifices all the convenience of automation. So the question is this: why is the fundamental 4 times difference in performance, that massive jump in effective range, linked directly to the fact that one weapon uses the automated high-volume gas system, while the other requires the operator to manually manipulate every single moving part before firing? Ponder the connection between human effort, mechanical simplicity, and ultimate ballistic performance.